It's time to combine what we know about complex numbers with what we know about vector spaces. In this chapter, I'll introduce you to Hilbert space, a term that can be applied to many different types of vector spaces, but is usually reserved for complex vector spaces like the one we're going to meet today. I think you'll find that the concepts aren't all that new. They're ones you've been studying over the past 10 days, just dressed up in new clothes with a few new names. First, let's check in with our friend the qubit, or at least the symbols I promise I will someday define for you. What do we know so far? Well, we know that alpha and beta are complex numbers, and that the sideways houses are vectors. So the right-hand side looks like a superposition where the scalars are complex, and the left-hand side is just the name for the superposition vector. It seems like, in order for all this to work, we're going to need a vector space that has complex scalars. That's going to be C2, which I spoke of briefly a couple chapters earlier. C2 is a two-dimensional vector space over the complex numbers, and I'm going to tease you with a peek of where we're headed next week. The coefficients alpha and beta are going to have a certain interpretation. When we square their absolute values, they'll turn into probabilities, numbers between 0 and 1. These probabilities tell us what our chances are of obtaining a particular measurement when we look inside the qubit's memory location. That's kind of interesting, right? The idea that we can't ever know with certainty what we'll get when we read the contents of a quantum bit, even one that we've carefully prepared. Well, that's all future talk. Meanwhile, let's get back down to Earth. There's no reason for us to restrict ourselves to two dimensions when we learn about Hilbert spaces, so rather than define C2, we'll be looking at Cn for any positive integer n. The vectors will be columns with n complex numbers in them. We call them n-tuples, and except for inner products, everything works as though we were looking at Rn, the n-tuples of real numbers. So what's different about these new inner products? They can't be the simple dot products that we have in R2. That won't work. We have to take the complex conjugate of the first vector before we dot it with the second. You'll see plenty of examples. Of course, there has to be some new notation for this inner product just to make our lives miserable. But everything we studied, norms, distances, orthogonality, even computing expansion coefficients, carries over exactly as before. We just have to remember to use this slightly revised inner product. Remember that dot with the basis vector trick you learned? Well, that's really important in these complex vector spaces, so I'll do a few examples and offer you some nice exercises. When we finally get down to describing a Hilbert space, it will turn out to be a bit more technical than I advertised. Yes, it will be a vector space and it will have an inner product, that optional feature that we always order, the leather seats, so to speak. But it requires a second property to really earn the name Hilbert. This space will have an annoyingly abstract convergence property. Now, you won't ever get into this, so I marked these sections optional, but I drew some pictures in case you're interested. Eventually, I bring us all back to the simple and safe C2, the basic two-dimensional Hilbert space of quantum computing. But I couldn't resist tempting you with an example of an infinite-dimensional vector space, a Hilbert space that's presented in your first quantum physics class. Its vectors are complex functions, and it has a fascinating inner product that uses integrals. Hilbert spaces have an interesting property called the triangle inequality. We'll talk about that briefly. And by the way, this triangle inequality is key to something you may have heard about, the Heisenberg uncertainty principle. So, other than a few optional sections that have perhaps overly abstract concepts, all we'll be doing this chapter is establishing C2, the ordered pairs of complex numbers, as a Hilbert space with the inner product that requires we first conjugate one of the two vectors before we dot them together. Except for one final important idea. When we get to quantum mechanics in a couple days, you'll see that all the vectors we really care about have to have length 1. You can picture this by imagining that we always use vectors that lie on the unit sphere in complex 2 space. Now, a unit sphere is the set of all vectors anchored at the origin that have length 1. It's called a sphere because the tips of those vectors, when you take them all together, make the shape of the sphere. Now, the Hilbert space C2 contains vectors that are both on and off that sphere. But if we ever get one that's off the sphere, we'll just project it onto the sphere, that is, we'll divide it by its magnitude. Why do we do this? Well, it'll be easier for me to explain next week, but roughly it relates to my introductory remarks. Remember, I said alpha and beta will have square magnitudes that are interpreted as probabilities. Well, the probabilities have to add to 1. That's like saying if you flip a coin, you get either a heads or a tail. Or if you roll 2 dice, you have to get a number between 2 and 12. This physical requirement, when you look at it mathematically, means that all the important vectors in our Hilbert spaces must live on the unit sphere.